Hello students, hope you all are doing well. You all are warmly welcome to the chemistry lesson here regarding second unit that we are going to talk about the resonance structures here. We are going to find out what resonance structures are. They are standing for molecules or ions. Okay, hope you could remember our earlier lessons. In that we talked about how to draw Lewis structures. Lewis dot dash diagrams standing for those given molecules or ions. We talked about that. Then students, it's the extension of the same lesson. Imagine if you found out that there are few Lewis structures you could possibly draw standing for that particular molecule or ion. What then you would do there? Then it's only one Lewis structure. They would ask you in a question paper or somewhere. So then you would then just be drawing one structure saying this is the Lewis structure and leave. Then students, in that, if you feel it like it's not only this, but also this possible. A possible structure that we could draw. Then it's many such structures if you could draw standing for same molecule or ion. Then we name them as what? Imagine, guess. So it's the resonance structures. Students, it's what we are talking here about. What are the resonance structures and how to get those different various resonance structures for the same molecule or ion. Okay, let me show you where do we have these all stuff in our syllabus. Okay, students, it belongs to competency 2. So says that relates bonding and structure to properties of matter. So there you have further, it's saying competency number 2.2, they are saying analyzes the shapes of covalent and polar covalent molecules and simple ionic groups. That's what we have got there. Then its subject content, when you check for, you would find that out. It's the concept of resonance structures of the simple molecules or ions, right? So using Lewis dot dash structures. So we are going to find out, we are going to draw resonance structures in our effort to draw the Lewis structure standing for that particular ion or molecule. Hope you could remember. So let me remind you, recall your memory regarding what did we do for the last time. Students, we started discussing or finding out what's the suitable way of representing that molecule with like bonding with a dash or short line. Then it's non-bonding electron, non-bonded, let's say, electrons with a pair of electrons or single electrons, sometimes rarely it's possible to be there. So students, we named them as the Lewis structures, drawing of the Lewis structures. We learned the art how we could draw those Lewis structures standing for given such either molecules or ions. So then it's a gentle reminder like what a Lewis structure. Students, a Lewis structure, it illustrates these things. What? It's the atomic skeleton, means what would you get throughout the molecule or ion, how those atoms are bound, which atom has bound to which atom. Such information, such details, it reveals there by the Lewis structure. So it's not only that, but also the nature of bonding. Nature of bonding present there as single bonding, for sometimes double bonding, triple bonding, such nature of bonding. Between these atoms you get a double bond. These atoms, it's a single bond only. These two atoms, it's a triple, like that. You won't ever get 4 bonds between 2 atoms. Okay, then students, it's the distribution of the valence shell electrons around each atom of the given chemical formula. So those informations, hope you could remember still, those information reveals there with, you could reveal those with a Lewis structure. When you find a Lewis structure, you could easily recognize what's the skeleton, which atoms have bound to which atoms, right? So it's how many bonding you have and what's the distribution of those electrons. Sometimes charges you could find, they are throughout Lewis structures. Okay, then students, it's drawing Lewis dot dash diagrams, it's we found that out, bond electron pairs with those representing with short lines, and those other electrons with dots. That's why we call that Lewis dot dash diagram. So then it was, let me recall your memory regarding few molecules and ions. Students, let's say it's carbon dioxide. So when you draw carbon dioxide Lewis structure, you need to first find it out the total number of electrons that you have with carbon. It's in its valence shell, it's 4, the total number of electrons you get there, and each oxygen belongs to 16th group, therefore 6 electrons, you have such 2 oxygens, therefore it's 12, the number of electrons given by each oxygen. So it's 16 the count total. So then the number of pairs would be 8. Then you decide the skeleton. Out of these, oxygen and carbon, in that competition, their electronegativity we need to consider. Students, the atom with least electronegativity is the central atom, except hydrogen. So it's hydrogen and fluorine, they are having just a chance of carrying one bond only. So therefore we do not give hydrogen and fluorine normally to the central position. So anyway, it's carbon here with the least electronegativity. Then other 2 atoms, I'll say it's oxygen. So then this is the skeleton. After drawing the skeleton, you deduct number of electron pairs out of total pairs that it takes by the skeleton. Then students, you place all the other electrons as you complete the octets on first most electronegative atoms. Here its terminal atoms are the most electronegative, so therefore it's 8 electrons now when you place 3 pairs of electrons, lone pairs we call them then. So it's then here the remaining number of pairs is 6, so after placing 3 pairs here, 3 pairs here, 6 minus 6 all gone. So you do that till you show all the electrons there. Then after it's the finding out of formal charge. Formal charge means they have got their own number of electrons in their valence shell. So it's 6 with oxygen. Now you take a count and find it out whether it's 6 still. So if it is not, then you assign a formal charge on that. Then students, here it's 1, 2, 3, 4, 5, 6. With this bonding, it's another 1 electron, so it's 7. But it has to be 6. So 1 electron has taken by oxygen, therefore 1 electron is in excess on oxygen, therefore it's minus 1, the formal charge on oxygen. So when you take this oxygen also minus 1, then students, it's carbon. Carbon is having 4 electrons there in its valence shell. Okay, now currently it's having 1, 2 bonding only, so each bonding is giving 1 electron, means carbon is investing 1 electron in each bonding. Therefore, it's 2 electrons only you could see here. Therefore, it's 2 lacking. The formal charge is 2. It's not just 2, it's plus 2, plus 2. Then next is the rearrangement. Rearrangement of electrons. Rearrangement of electrons minimizing their formal charges. How could we do that? It's students, you could easily try that drawing dative bonds. Then you use this pair of electrons there on oxygen and you erase that and use it in a dative bond. Donor would receive a +1 charge and accept a -1. You do the same with this pair. So it's donor +1, accept a -1. All the charges are got cancelled off. Okay, then students, it's finally what you could end it up with is this. See how easy? That's how we learned last time how to draw Lewis structures, Lewis dot dash diagrams. You got various some other diagrams as well, but we are normally drawing Lewis dot dash diagrams. What are the others? Others are Lewis dot structures, Lewis dot crosser structures, and such various other structures also you could draw. Okay. So let me brief this thing. How to draw Lewis structures, Lewis diagrams, Lewis dot dash diagrams. Students, in that you need to first take a count of total number of electrons, actually electron pairs in the valence shell available. Secondly, you draw the skeleton. Skeleton, it's you name one atom as the central atom if there is one central atom. Then otherwise it has to be provided details, informations regarding what's the skeleton. If it is many atoms, not one, being the central. Okay, so then it's you draw the skeleton, least electronegative atom is more suitable with that. So then it's you mark the formal charge. You first mark the number of pairs of electrons, then after you mark the formal charge. It's the order. It's students, it's you first mark all the electrons as given octaves on more electronegative atoms. Then after only you need to mark the formal charge. I have showed you already. Okay. Then students, you could next after assigning a formal charge, you could rearrange those electrons. That's how you could draw what? It's the Lewis structure. Just imagine if it's possible you to find it out, this also is better as a Lewis structure. Why can't we draw it in a way like this? Why it is not suitable this as the Lewis structure but this? If you have got many such problems there with you, it's not just your own problem. It's just you need to know the theory. You need to know how to get the proper Lewis structure in one hand, and in the other hand, how to decide which one is more stable out of those all the possible Lewis structures, which one is more stable. It's very important. Very important. Okay, students, then it's our first effort is to find it out. What are the possible various structures? Let's not name them as the Lewis structures. What are the possible various different structures standing for this given molecule or ion? What are the possible structures? Then after let's do that, we'll find it out their relative stabilities. There are relative stabilities of those each structures. Then we need to know how to get that, how to find it out, the relative stabilities. I'm going to show you how to get the relative stabilities. Then it's finally, after having such Lewis structures, if you finally find it out, not certainly as this is the only possible Lewis structure, all the Lewis structures are equally stable. If you end it up with something like that, then students, what would it be the real structure? True structure. Then you would start thinking of that. Okay, you don't worry on that as well. Students, we are going to draw something representing those all based on their relative stabilities. So, representing their relative stabilities, we are going to draw one structure. Let's call it the combination of all or mixed up of all. What's the mixed up means in science? Mixed up, having two properties together. It's we call hybrid. Let's draw the resonance hybrid at the end. That's our target. That's our goal. Okay, so it's my duty is to guide you towards that. Okay, with that, let's start our job here. Students, you could here find it out, resonance structures is the possible. It is possible to draw a number of Lewis structures for a certain molecule or ion. So these Lewis structures with the same skeleton or atom position are called resonance structures. I mean, it's actually the same idea that I have already given you. The most stable resonance structure is the Lewis structure of the molecular ion. Anyway, it's the same idea that earlier I have taught. So then students, it's when you go ahead, let's find it out how to handle this. How to handle what? How to handle SO3 2 minus. So it's, I will use all those I will work out in the procedure as how to get a Lewis structure as first I need to find out total number of electrons pairs, then in the main in the valence shells all the valence electrons we call that. Then after we need to know what's the skeleton. Then after we need to arrange those lone pairs there on most electronegative, starting from that in the descending order of their electronegativity. Then after it's we need to assign charges, formal charges. Then after it's we need to rearrange. Doing all those, it's I could find it out in this way. It's S O3 2 minus could have its possible Lewis structure like this -1 -1. Then its SO3, same SO3 could have the double bond here. So it's -1 charge here and -1 charge here. It's another. Students, we are going to draw an arrow. This is a very, very special arrow. This is used only to denote resonance structures. In drawing of resonance structures only we use this arrow. It's special. So then next I could change the position of the double bond. It's once I have used it here, then here, where else? It's there, right? So at the next time, this is a resonance structure I'm going to draw there. So it's the arrow that we use there to say these are the resonance structures. So it's we have S, then the same skeleton, but the double bond comes here. Then these are like that. So it's students what you get as the resonance structures standing for SO3 2 minus. Then it's you would learn later on these are equally stable resonance structures. Then it's further in our way to draw the resonance structure. It's I could draw something like this as well. It's same skeleton still, but this is not at the end I get. At the very beginning, seeking a resonance structure, seeking a suitable Lewis structure on that I would be starting first drawing the skeleton, then placing those pairs, lone pairs, first with more electronegative atoms, giving them octaves, then in the descending order of electronegativity, remaining lone pairs. Then students, you could find that out at the very beginning, drawing something like this, right? So you would get +1 here the charge, -1, -1, -1. This also we could consider as another resonance structure. One could argue like, why it is not possible to be a Lewis structure or resonance structure or something. So yes, it's also possible structure. So all the logical possible structures are called what? Resonance structures. Now, hope you have got an idea regarding what kind of structures could be like these resonance structures. Students, in your effort to represent its structure, you would be doing something like this, thinking you are going to draw a Lewis structure. You would be first counting up the total number of valence shell electrons. Thereafter, you would be dividing that by 2, then saying this is the total number of electron pairs. Then you would be drawing the skeleton. Then after placing those pairs, let's say as lone pairs, on first more electronegative atoms, then in the descending order of electronegativity. Then after assigning the formal charges on those atoms, then rearranging those pairs, as to minimize those what? The formal charge, overall charge. Then the more stable one is taken as the Lewis structure. Others are just the resonance structures. All of those are the resonance structures on your way to draw the structure, what you get logically. So students, it's relative stability of resonance structures, it's very important. It's very important on saying this is the Lewis structure. These are just resonance structures only. Then how would you decide which one is more stable and which one is less or least stable? Students, in that, it's very important counting up of total charge. So it's we need to find it out the overall charge on each atom. You might have placed already a charge there in various structures, various resonance structures. You might have got already somewhere a charge. It's regardless of positive or negative, you take them all as considering those, it's just one time. So if it is minus 1 and plus 1, you take it as 1 and 1. It's then 2. You add them up, you take the count of total charges. So not worrying about their sign. Then students, you need to first take the total number of charges. It's very, very important on deciding which one is more stable. In that, when you have less charge, less number of total charges, that's the best. Charges make them unstable. Neutral is the best in this aspect, not always. Okay, charges make them unstable. Regarding atoms, I'm saying, right? Charges make them unstable. When you have more charges there, it's more unstable. Less charges there, it's more stable. Less unstable is more stable. Okay, so therefore the number of charges is very, very important critical factor. It's the first most important. So if you have two structures with two different number of charges, the one with less number of charges is the best, it's the more stable. Then it's the separation of charges. What's the separation of charges? It's a charge is a trouble. A charge is a trouble that atom is having. If you find it's let's say 2 or more charges on the same atom, then against that means it's exceptionally if you have, optionally if you have another way of representing the same as it's those charges were being shared, were being separated between two atoms. That's the best. Students, it's one atom would not like to take all the troubles with that. It would be better if you give them, if you share your troubles with others, right? So it's, I might be very bad saying this, but at the very beginning when we have heard that, it's we have met with some accident, like let's say it's the disaster tsunami. So it's if it happened to you, only you yourself, then it would be terrible. It would be very, very terrible thing. Now also it's terrible, but it has generalized. Its whole community got affected. It's very bad saying that, but it's then it after generalizing, it's not only on me, it's on others also. It's possible. It's possible. Therefore, it's quite stable than having all the troubles on yourself only. It's another example, Kisa Gautami you take. Students, it's seen that all the troubles faced by herself only, like those children got died. So it's those many various troubles, more other troubles also she has faced. But knowing that all the others also have faced similar troubles, like they have got their own been have died already, so in other houses. So then it's quite okay. It's what I'm telling is very bad, but it's our mentality normally is. It's seen that it's not only on me having the trouble, it's all in the community are having such. Then we could quite like say it's okay, then it's okay. It's anyway, having a trouble it's making you unstable. But students, it's having all the troubles on one atom, it's making unstable very, very, very highly. So it's distributing the troubles. Trouble means the charges. Distributing of charges make them what? It's make them quite stable than that. Okay, that's what I have mentioned as the separation. Not carrying all the charges on one atom, but sharing those charges there. So like then it's the distribution. Is that the same that as of earlier? No, it's not. Students, it's you need to check for on which atom I have placed the positive charge. On which atom I have placed the negative charge. That's what we call the distribution of the formal charge. What's that? It's if it's a negative charge, those more electronegative atoms would more likely take the negative charge than less electronegative atoms. That's the point. That's the point. So it's there are suitable characters in the society for some various different things. It might be difficult as well, but they would face successfully than others. So then we need to find it out, the suitable character carrying the charge. More electronegative atom would carry the negative charge so easily than less electronegative atom. Vice versa of that is, more electronegative atoms would not like to take the positive charge on it. Compared to that, it's less electronegative atom, it's better giving the positive charge on less electronegative atom. So these few things are the important when we decide which one is stable and what's the order of stability. Okay, so let's find out few examples standing for those points. What's the first point? Is the number of charges. Number of charges. Students, when you get number of charges, it's the most stable resonance structure has the least number of formal charge. So contains the greater number of covalent bonds. Contributes mostly to the resonance hybrid. It's very important. It's very important. On this, both of the maximizing the number of bonds and satisfying the octet rule should be achieved. Okay, those are the requirements you need to think about. They are giving charges there. So it has to be less the charge. Okay, let's find it out how these factors could affect on the stability. Let's consider the very first factor. There, it's the total number of charges. Then students, what I have taken as my example is sulfate, the well-known anion. Hope you know that. So its sulfate, students, is carrying sulfur and oxygen. When you take the total number of electrons, they are starting drawing the Lewis structure. Its sulfur is given 6 electrons and oxygen 6 into 4 is 24 electrons plus 6 electrons is 30 electrons plus 2 electrons by the charge is 32 electrons. Divided by 2 is 16 electrons. You get 16 electron pairs there in the valence shell of this anion. Then students, when you reserve it's the skeleton with 4 bonding, so it's another 12 electron pairs it is having. So out of oxygen and sulfur, sulfur obvious is the least electronegative. So therefore, let's place that to the central position. Then you have 12 pairs of electrons. On each oxygen, the most electronegative out of these two, placing 3 electron pairs as reaching octaves. So all 12 you could finish. Okay. So then students, you could start marking the formal charges on your way to draw the Lewis structure. But at the very beginning you would find it's 7 electrons, therefore -1, -1, -1, -1 on each oxygen. Then it's 6 electrons has to be there, but 4 in bonding. So it's 2 lacking, so it's +2 the charge. Then it's +2, -1, -1, -1. So then when you count it out, the total, it's 4 + 2, regardless of the sign there. It's 6, the formal charge, the total charge. Then students, you could minimize the formal charge or total charge, giving a rearranging electrons, giving a dative bond from this oxygen towards sulfur. Then it would become +1. Now sulfur is having no charge on that oxygen. It's -1, -1, -1 still. So it's 4 the charge here. Then rearranging another pair, you could draw another dative bond there. So then it's you have 2 the charge there. So then charge varies 6, 4, 2. Out of those, the least value is 2. You need to know out of 6, 4, 2, which one is the least. Okay, right. So it's 2, not 4, not 6. This is the most stable, most stable structure. These are 3 resonance structures. When you consider their stability, so having less charge is making it more stable. It's the most stable structure. Then this is the second most. Then this is the third most stable structure. That's how we handle the overall charge, total charge, number of formal charges. Let's go to the next. Next is the separation of the formal charge. So here it is more stable if the number of total formal charge is separated, giving a lesser formal charge on each atom. What I told earlier, it's the same. So structures in which adjacent atoms have formal charges of the same sign tend to be unstable. Let's find it out what it is saying. Then it's a separation of formal charges. You could find it out there in this ion. What's the ion? It's N3 minus. What is N3 minus? It's A site anion. So then students, you could find there in motor vehicles, within airbag, you could find sodium A site being stored. So there would be electrically induced or catalyzed dissociation reaction they are having after met with an accident. It's then forming nitrogen there. That nitrogen fills inside the balloon, so you get the air balloon being filled. Okay, so anyway, it is sodium A site. This is A site, the anion. So students, you could represent that either in this manner or this manner. What's the wrong with these two ways? It's nothing wrong, but the same formal charge, same number of charge. It's 1, 2, 3. 1 and 2, it's 3. Here it's 3, here it's 3. But here those 3 charges are carried by 3 nitrogens. Each nitrogen is having 1 charge only. This nitrogen is resting, it's relaxed one. This nitrogen is carrying 1 charge, but this nitrogen having the weight fully on it. So it's highly unstable. It's better having the separation of charges as it's distributed throughout atoms. Each atom carrying charges is better than one atom is carrying more charges. So this is more stable compared to that. That's the point. That's what we call separation of the formal charge. Then students, it's the distribution. It's the distribution of this formal charge. You need to check for which atom has got the formal charge now. So when opposite formal charges are placed on adjacent atoms, positive charge should fall on electropositive atom and negative charge on electronegative atom. That's what. When positive formal charges placed on highly electronegative atoms such as F means fluorine and oxygen, the structures are unstable. You don't treat such prominent atoms. Prominent atom means most electronegative atom in the world is fluorine still. So you don't place a positive charge on that. That's a mistake, big mistake. So then second most electronegative atom is oxygen. Don't place positive charge there as well. Okay, that's the point. Then students, it's when you check these, it's you could find it out. It's +1 and -1. +1, -1, +1. So what's the difference between these two? It's you have central atom in both carrying just +1. No difference there compared to these two structures with its central atom. But here oxygen is carrying a -1 charge, but it's here it's nitrogen at the other end. So then let's treat oxygen as it's the most electronegative atom. So let's treat oxygen with the negative charge because it's capable of carrying the negative charge better than nitrogen, means more than nitrogen. That's the point. That's the point. Therefore, this is more stable. That's what we could learn there regarding the distribution of the formal charge. Okay, let's find out an example stand-in for this. Students, it's sulfate, this anion. So sulfur is carrying 6 electrons in its valence shell, into 2 is 12. Oxygen 6 electrons in its valence shell, into 3 is 18 plus 12 is 30. So with -2 charge, it's 2 electrons, it's 32 electrons. Divided by 2 is 16 pairs of electrons you have there. It's in their valence shells of all those atoms. Then out of sulfur and oxygen, its sulfur is less electronegative, so let's take one sulfur to mid position. So then its skeleton I could give as 3 oxygen atoms there, the other sulfur atom there. Then students, distributing those electrons with 4 bonding, it's 16 there were. So it's 4, you deduct 4 there, it's 12, another 12 it remains. You place those 12 electrons as 3 pairs, first on each oxygen, then it's 9 pairs being used. Let's place another 3 remaining 3 on this sulfur as well. So then it's done. So then students, it's the charge here -1, -1, -1, -1 for the reason that they normally have 6 electrons only, but in these they have 7 electrons with the electron in the bonding. So its sulfur needs to have 6 electrons, but it's having 4 electrons given by those 4 bonding. So it's +2 the charge on sulfur. So therefore this is the very first structure that you could draw with the formal charges. Then let's rearrange. Let's rearrange those electrons. When you rearrange electrons, you could draw it either in a way like, so it's you have sulfur here, oxygen, oxygen, oxygen. Let's give a dative bond here and another dative bond somewhere. So you would get still -1, -1. So then these two have no charges including sulfur. Then it's one possibility. Someone could think like, why is that by sulfur the dative bond is given? Let's give the dative bond by 2 oxygens. In that aspect, you could find another possible structure standing for this. It's sulfur. So it's these two, let's say, are giving their pairs to form dative bonds. It's pi bonds then. So it's this sulfur and this oxygen still remain as carrying -1, -1. My point here is compared to these one structure to another, it's you could find out it's both minus charges now on oxygen there. But here, though you have here a minus charge on oxygen, it's students, you have here minus charge on sulfur. That's the difference. It's you have a minus charge here on sulfur, in the other one on oxygen. Then what out of those two, which one is more electronegative? It's oxygen, right? Then it's having the minus charge on oxygen rather than sulfur is better. This is the more stable structure compared to this. That's the stability we decide based on the distribution of charge. We check for the charge of, means if it's a negative charge, which atom is more suitable to carry the negative charge. If it is more electronegative atom, it's better. Then if it's a positive charge, if it is a less electronegative atom, then it's better. That's how. Then it's students, additionally, it's we have such situations as well. So when you have two adjacent atoms carrying the same kind of charge, same charge, so it's plus and plus makes them unstable. So it makes them, these two come here and these two break. So this is an unstable structure. So at the next time it's going to be broken. The bond going to be broken. So having of equal charges or same kind of charges on two adjacent atoms make them unstable. You need to know that as well. Okay. Then students, we are going to find it out one structure that could represent all those structures. All those structures mean we found out resonance structures. We found out various resonance structures being possible to be drawn for one particular molecule or ion. Then out of those all the possibilities, they might be differently stable. Then students, representing all of those, if you have a representative structure, that's what we call the resonance hybrid. In that, we give the priority on more stable in the decreasing order of the stability. Their contribution towards the representative molecule, what we call the resonance hybrid, their contribution is more if it is more stable, the structure, resonance structure. If it is less stable, their contribution would be less. That's what you need to know here. It is the common representative of all the resonance structures. The contribution to the resonance hybrid is less by the less stable resonance structures, is more by the more stable resonance structures. Then when you draw the resonance hybrid, you need to make that sure whether you are checking these. You need to study all the resonance structures. Then students, you need to state those common bonding that you find within the resonance structures, like all the resonance structures that you are going to take to the count. So you check for all of them. Obviously you would have the skeleton within all of them. Then for sometimes additionally you could find out some pi bonds. You find within all the structures. This pi bond is there within all the resonance structures. You mark that pi bond there in the resonance hybrid as well. Then further, if you find some lone pairs on some atoms being not changed, unchanged, then place them on the resonance hybrid. Those features are common, need to be shown there in the resonance hybrid. That's the principle, that's the concept. Then if you find a charge being unchanged, you please place that. They are on the resonance hybrid at the same place. Then students, if you find it out, some pi bonding got changed there. So you have this pi bond there within that structure, but in this resonance structure you don't have that pi bonding. Then students, what you need to do is such pi bonds you need to show with dot lines. That's what. Then counting on charge. It's if you notice one atom, it's this atom. Once it has got a negative -1 charge. Now it's in this structure it's 0, and in the next structure it's +1, and in the next structure it's +2 or something like that. So what you need to do is you add all those charges including 0. Then you take the total. Then you find it out number of chances, means how many chances that you have considered. Then you divide the total charge belong to that atom by the number of chances. Then it's the average you are giving. You give the average charge on each atom. It's possible you to mark the charge on each atom individually, or it's not marking those there. As the final charge, overall charge, you could mark there, placing the resonance hybrid there within a square bracket. It's out there, you could mark the charge. I will show you that. So students, that's what you need to know when you start giving the resonance hybrid. It's better if you represent the shape as well. Okay, then look at this. It is sulfate. This sulfate is once having minus charges here and minus charges there. These not only two resonances possible, some other resonances also are possible. So to separate and show them, they are the resonance structures, that unique arrow I will use. So here also I will use. They are the resonance structures. Then students, it's representing all these resonance structures. You have the skeleton. Skeleton means at least one bonding, at least a single bond you have between sulfur and oxygen at all the times. But it's not always you are having this double bond between this sulfur and this oxygen. Therefore, you need to show those pi bonding with dot lines. Okay. So in that manner, you could draw the resonance hybrid either in this form using dot lines to show those pi bonds. And when you check for the charge, it is -1 and -1. It's not here -1. It's all together. It's 6 structures. -1, -1, -1. It's -3 divided by 6. Is -half. Is the charge belong to each atom? So similarly, you could mark the charge on each atom. Then it's no charge on sulfur, you get. Then students, it's not marking those charges on atoms, it's you add them up. -half, 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 -half. It's 2, -2. So you give the -2 charge at the end, right? As it's the overall charge, not marking charges there. So it's as I have told you that it's better if you show the shape as well, but it's not a must. This is sulfate, SO4 2-. Okay, students, let me show you an exam question given. It's a structured essay. In year 2020, it was given as the first question of structured part B. So saying it's draw the most acceptable Lewis dot dash structure for the iron. It's N2O3 2-. Its skeleton is given below. Let's draw the Lewis structure for this. Let's first find out the total number of electron pairs in their valence shells. Students, you have 2 nitrogens. Each nitrogen is given 5 electrons, into 2 is 10. So oxygen is given 6 electrons in its valence shell. You got 6 electrons, into 3 is 18 plus 10 is what? 28. Plus these 2 electrons, it's 30. 30 divided by 2 is 15. You have 15 pairs of electrons. Then students, it's 1, 2, 3, 4 bonding already reserved out of those 15 pairs. Therefore, it takes 4 pairs. Therefore, it's 11 pairs only you have got so far. So then it's, if we first mark those pairs, 11 pairs, as on most electronegative atoms there as 1, 2, 3, 4, 5, 6, 7, 8, 9, right. Then it's another 2 pairs those atoms have got. So let's place those on those 2 atoms. Then students, it's I have done that, giving 8 electrons on nitrogen and remaining pair only I have placed on this nitrogen. Then let's mark the formal charge first. It's -1. It's -1. It's no charge you have. It's you have +1 the charge here. Then students, it's -1 the charge. Then let's rearrange those electrons. It's better if this nitrogen get an octave. So let's use this pair. So use that as to form a dative bond. So it's a +1 the charge and it's a -1. So finally you need to have the charge being -2. So it's then matching. Okay. Then what you would get finally is being something like this. You have a double bond here. So it's, you have got it as -1, -1. It's still a lone pair. So it's you have another lone pair here. So it's this. This is the most suitable structure, or the stable structure we could call that. Then students, it's in the same question, they have asked that to draw resonance structures as well. Okay, draw 3 more Lewis dot dash structures, means resonance structures for this ion, indicate the relative stabilities of the structures drawn by you when compared with the most acceptable structure drawn in question number part 1. So it's above. Write less stable or unstable under these structures. Okay students, it's what we have so far recognized, it was this. Naming it as the Lewis structure. What they are asking us to do is, they want us to draw resonance structures. Resonance structures stand in for this. This is the Lewis structure. This is the most stable structure. But further, they need some other structures, suitable other structures as well, stand in for this. Right. You could use this pair as to form a dative bond. Here means a pi bond there would be between these 2 nitrogen, and you could shift this pi bond there towards oxygen. So with the same skeleton, it's you have a pi bond here, then still it's you have these as -1 the charge here, -1 the charge here. But here it's a +1 after that dative bond, using this lone pair, giving that lone pair there, forming a dative bond as a pi bond. So it's, then students, you would find this still carrying a pair. It's a new -1 charge here. So here the overall charge is 1, 2, 3, 4. It's 4 charges. Here you have got 2 charges only. Therefore this is more stable than this. So anyway, we could further draw some such structures as thinking on, it's you could give a dative bond from using this lone pair. It's, you could make it like this. Students, when you draw another possible structure, it would carry a -1 charge here, +1 charge here. It's possible you to have -1 here and -1 here. So then it's another resonance structure. So it's, we could interchange the double bond this to this. So in the next resonance structure, it's, we could draw it in a way like, still carrying the -1 charge here, it's still -1 charge here. Now the double bond is there, it's a +1 charge. Then it's a -1 charge. So then students, these are the possible structures. I'll call them resonance structures. In the question they have asked us to mark them as unstable and less unstable. When you compare these all, you could find that out all are having 4 charges. Therefore, all compared to this are unstable. Then when you compare this with these two, students, you could find in all these having a plus charge on nitrogen. So it's not a difference that you could find, notice there regarding those 3. But you have minus charges here. It's a minus charge on nitrogen in these 2 you are having. But minus charge is all the 3 minus charges you could find on oxygen. Then more qualified for minus charges is more electronegative atom. Okay students, in that aspect this is the less unstable and these are the unstable, more unstable, more unstable. Okay, in that manner you could solve such problems, such questions given in the exam. Students, it's very easy part that you to decide what's the Lewis structure and what are the possible resonance structures there. Then it's representing all the possible resonance structures. When you draw one, it's the resonance hybrid there. Then students, with that we have come to the end of our lesson. We are going to wound up here saying that if you want to watch this again and again, you could visit us there in YouTube channel NIE. Okay students, goodbye.